In chapter 8.3, we start with our observation that we found in the previous chapters and we work on them. So first of all, the idea is to start with m r double dot is equal to 0. How is it derived? Well, it's derived with the fact that we imagine there is external force is equal to 0. Therefore, the acceleration, which is equal to, in our case, r double dot is equal to 0 on our central mass. Now, why is the central mass 0? Well, because if we imagine something like this, and we have the center of mass at the center, then with an inertial uh, resonant frame, as the center of mass moves, not accelerated, then we can move our inertial reference frame wherever the center of mass goes. So it doesn't. It's important to remember this because it tells us that the acceleration is going to be equal to 0, even though the velocity is going to be equal to a constant because the center of mass can still move and we can keep our reference frame the same. So since our whole system equation does not accelerate, but it moves with certain speed, then our center of mass does not accelerate either. Okay. Now, of course, our Lagrangian then becomes equal to 1/2 mu r dot squared plus u of r. Sorry, actually minus u of r. So if we solve this, we get r equals d over dt. Oops. R dot. Okay. So on the left, we're gonna get negative u of r. Actually, sorry, the derivative of this, which will be equal to negative divergence of u of r, both equals to d over dt, and then we get mu r dot. And if we derive this, then we're gonna get for the left side, well, the same because it doesn't matter right now. It's equals to mu r double dot. And as you can see, we just derived what the book is saying. So as I said, then we can imagine an inertial frame that moves with the center of mass, and then we have to use all the things that we know already by this graph right here to find a center. I'm gonna do this right now to find the angular momentum. Actually, well, we know the angular momentum is equals to r1 cross product with p1 plus r2 cross product with p2. Now all of these, of course, are vectors because there's a cross product. And this is an algorithm for the whole system. We always, of course, care about the whole system. Therefore, right now here, if we rewrite this, well, we know that P1 is equals to M1 R dot 1, R1 dot. And of course, P2 is equals to M2 R2 dot. Okay, so and we also know that R1 is equals to this value that we have right here. There with this circle, and R2 is equals to this value that we have right here. So if I substitute in there, I get that it's equals to, in this case, M2 over capital M, R vector, cross product with M1, of course. Then R1 dot is going to be equals to M2 over M, R dot, plus R2, which we know is equals to, I calculated there, M1 over capital M, and then R cross product with, M2, and then times R2 dot, which is equivalent to M1 over M R dot, of course. So let's solve this thing. First of all, we can take all the things in front, and I'm gonna start with actually M2 times M1, and then there's another M1 that we have, another M2. I'm gonna write like this right now, over M squared times R vector cross product with R dot vector plus, in our case, that we get M1 times M2, then outside the parentheses M1 again over M capital M squared, And then the same thing that we got before, so parentheses of R vector cross product with R dot vector. There we go. So one thing I want you to look at is, if you remember from the previous chapter, M1 times M2 over capital M is equals to our reduced mass. So we can substitute part of it in here. We get that it's when we go to our reduced mass times M2 over capital M is equals to R vector cross product R dot vector plus, well, same thing here, so reduced mass times M1 over capital M times R vector dot cross product with R dot vector. Okay, so we can take what's in common. I want to take, for example, the reduced mass over capital M. Reduced mass over capital M is equals to, times M2 cross product with R. Actually, let me copy from here. It's gonna be faster. There we go. Plus, in that case, M1, and then same thing again. So as you can see already, you can simply group this inside parentheses again. So that equals to our reduced mass over capital M times R vector cross product with R dot vector times M2 plus M1. So we know that M2 plus M1 is equals to our capital M, so it cancels out with what's outside here, and we get that our reduced mass times R vector was part of R dot vector, and actually here we can cancel out our parentheses, is equals to the angular momentum. As you can see, we solved the whole problem with the whole angular momentum instead of such a complicated part in just three factors, pretty much. The two of which are related to each other, and this solves all our problems. In the second video, instead, I will solve the last part of our problem, the last chapter, because I think it's a little bit more complicated.